Okay. All right. So we've done most of momentum. All right. We may come back and visit a few more problems related to momentum after we do the next topic, Bernoulli, because they're actually together. I hope it's recording. Okay. All right. So we'll come back to more examples later. All right. So today we'll do the Bernoulli equation. All right. All right. We'll do the energy approach. Well, I call it energy approach, and dynamic approach. Okay, how you get the Bernoulli equation, and then we'll do some examples, and then I think flight and aerofoil theory. Okay, so that's the plan. Okay, save. All right, all right. Okay, so hey, okay, save. All right, we'll quiet down a little bit. It's still very noisy, huh? All right. So I know it's late Friday, weekend close. Sorry, Thursday, weekend close. Tomorrow Friday, can go holiday and all that. But you know, you need a little bit more. Right? Okay. All right. So okay. So assuming this is your streamline, all right. So the flow goes along the streamline, all right. So this is the next streamline. Okay. So at any point, the flow is the velocity is tangential to the streamline. Okay. That's what the definition of streamline is. Okay. So there's no flow in this direction, huh? All right. So assume your flow go along a streamline. Then we assume, for the simple case, no energy loss. All right. Later we'll worry about energy loss in pipe flows and so on. But for now, no energy loss. ENERGY. All right. No energy loss. No, what else? Steady state. Steady state. And what else? Constant density. All right. That's our assumption. So this valid if your velocity much less than the speed of sound. Okay. Slow flow. All right. So in most cases, okay, you consider a blob here and a blob here. Okay, this fluid, all right, at some later point will have traveled here, point 1, point 2. Okay. Can we say that energy, all right, I'll do the energy approach first because it's easier. Energy approach. Okay. So the energy, can I say the energy is we all know there's kinetic energy. All right. There's potential energy. And there's flow energy. All right. I'm sure kinetic energy and potential energy you know already, isn't it? All right. Yes or no? All right. Flow energy comes from, all right. All right. So for a blob of fluid of mass m, Okay, kinetic energy is half mv squared. Correct or not? Alright, potential energy is mgh. H is some height based over some, here maybe h equals to 0, some datum. Alright, it's all relative anyway. Okay, as long as later on we use back the same datum, we are okay. H equals to 0. If you use different datum, then there's a problem. Alright, and flow energy, this is your pressure times volume. You seen before? Alright. For those who didn't see before, who didn't see before? Alright. Those who didn't see before, the flow got energy one. How does that come about? Because yeah, this energy, if you practice Tai Chi, this one has energy. Okay? Alright, imagine this flow. Let's say this is an arbitrary boundary. Okay or not? Alright? Some boundary. Okay? For the fluid to move along or to move into this region. Okay? Alright? So this is some arbitrary boundary. So for the fluid to be here, it must have to be moved into here, isn't it? Because previously, let's say it was here. Alright? So, to move the fluid, you need to push. Right? Like Tai Chi, push. Okay? So that push is force. So flow energy is force times distance. That's energy, isn't it? Alright? To push that blob of fluid into, so that it move ahead lah. Okay? Is that alright? Force times distance is energy, isn't it? Okay? So force, this force is equal to pressure times area times distance. Okay? So area times distance is volume, isn't it? So pressure times volume. And that energy comes about because to move the fluid, you need to push it along, or it is getting energy from the pressure. The pressure pushing the fluid, there's energy there. Alright? So high pressure, regions where the pressure is high, there's more flow energy. The pressure pushing, alright? Again, we are looking at this control volume. So the pressure pushing this one along, alright, has to move this fluid forward. We're considering just this blob of fluid. That's where the energy comes from. Okay? Is that alright? Right? So pressure, that's where the energy flows. Alright? You want to talk about other energy flow, you talk to your Qigong master. Okay? So, if no energy loss, steady state, okay, no energy loss, steady state, energy at 1 equals to energy at 2, isn't it? Alright? So, same blob of fluid along a streamline. Okay, no energy loss, steady state, no constant density. So, can I say this mass is actually half rho volume V squared. Okay, V is the big V is the volume. Alright, plus rho V GH plus pressure times volume. Alright, equals, this is at point 1, equals at point 2. Half rho V squared plus, the big V is the volume, the small v is the velocity. Alright, this rho times V is your mass. Alright, rho big V GH plus pressure times volume at point 2, constant. Alright, so I can cancel this off lah. Okay or not? Alright, so I can say half rho V squared plus rho GH plus P equals constant along streamline. Okay, that's your Bernoulli equation. Alright, so this is the energy approach. Very easy, isn't it? The only bit of a complicated part is that flow energy, the chi part. right? Because energy flows through, I don't know. Okay. Right, I can solve volume both sides. Right? So it's actually, all this is energy per unit volume. This is the kinetic energy per unit volume, potential energy per unit volume, and flow energy per unit volume. Okay, not? Okay. If you don't like this, well, an alternative, so this is the energy approach, is the dynamic approach. Alright? Dynamic approach means F equals ma, that's dynamic. Okay? So dynamic approach, a bit more complicated. Alright? Okay, so you need to look at the forces. This A is the total acceleration, total. Alright, we'll show you a bit later. Alright, the forces. Okay, this is your block. Alright, you can have the area here, A, on the back side. Alright, and I assume the area here is the same. Alright, and it is of length, I think ds. S is this path. This path is S. Right? Not X, not Y, but the path, along the path. Okay? Okay? Alright, so some of the forces, alright. So here we have the pressure here is P. Here the pressure is P plus dP on ds. Alright? Because the pressure might be varying along the streamline. So this is the pressure at point S, and then this is the pressure here. So the force is equal to pressure times the area. Alright, in the S, so these are all done in the S direction. In the S direction. Alright, pressure times area. Alright, minus pressure plus dP on ds times area. Okay, no? So this is the pressure in the front, in the back side pushing forward. This is the pressure. The next term is the pressure on the front side pushing back. Both sides are same area. Okay. All right. We have what other force? We have gravity. Gravity is mass. Plus or minus, then I put plus first. Mass, which is rho times area times ds. Is that right? A times ds, that's the volume, times gravity, g. Alright? But the direction, rho A ds times g, but we only want this component here. So if this was theta, you want this component, so it's cos, is it? Cos theta, isn't it? Cos theta. Alright? Is equal to, so these are the pressure force, this is the gravity force, equals to mass, so rho times A times ds times acceleration. Now, acceleration A, alright, is equal to A is equal to dv on dt. Correct or not? But the velocity is a function of both s and t. Right? Could be lah. Right? In general case, the velocity along the streamline, some parts of the streamline, the velocity can be faster, some parts can be slower. And At the moment, I'll leave the t there, but later I'll cancel out because it's steady state. All right. So dv on, okay. So actually, normally this one they change it a little bit. They put big D here. All right, because velocity is in function of both s and t. This is actually equal to dv on dt plus dv on ds on dt. Chain rule. Seen it before or not? Okay? Because velocity is a function of both s and t. All right. So the total loss, the actual A is actually due to, if there's this term, if the velocity changes in time, then they want dv dt. But if the fluid is actually accelerating along the streamline, all right, in other words, here is one speed, down here is a different speed, then this term is positive. There's also still acceleration, spatial acceleration. So in time, there's no change. So normally we do steady state. So in time, there's no change, 0. But if the fluid is actually, so this point, if the fluid is 1 meter per second, at some later time, it's still 1 meter per second, no change. But this point doesn't need to be 1 meter per second. This point, example, could be 2 meters per second. So this point, 1 meter per second. So when the fluid travels between here and here, there must be acceleration, correct or not? All right. So that's captured in this term here. All right. Spatial. So the fluid is accelerating. So from an observer point of view, everything is steady. But from the fluid particle point of view, all right, if you were that fluid particle, you will feel that you accelerate. All right. But the observer looks, every time you look there, that 0.1 meter per second, that 0.2 meter per second, steady state. Right? But if you were that particle piece of fluid, you would feel that you will go from 1 to 2. You feel suddenly your speed is 1, later 1.2, 1.3, 1.4 until you reach 2 meters per second. All right, and that's captured in here. So you need a force to capture that part also. All right, for that, although the system is in steady state, but for that parcel of fluid to accelerate, all right, there must be some force, and that force comes from here, pressure and gravity. Is that okay? Okay. All right. So again, I said steady state, so I'll kill this fellow off straight away. So we have dv on ds, ds on dt. Okay. So let's see whether hopefully can do. All right. Pressure area. This pressure cancel off. So I have minus. Actually, this one is also minus, minus cos theta. Because I resolved it into this direction, but when I resolve in this direction, this is actually this gravity is pointing in the minus s direction. Correct or not? All right. So I resolved it here. Okay, so this one minus dp on ds, ds a plus rho a ds minus g cos theta, and here equals to rho a dv on ds, ds on dt. ds on dt is actually, what is that? V, is it? All right. So it's actually ds, dv on ds, v. All right, not? ds on dt, that's the rate of change of s as a function of t, and that's basically your v. Huh? Huh? Which one term? Rho a ds. Yes, this is one term. Put a bracket here. Okay, can put just minus rho ga g cos. Okay. So let's see where I can tidy up. A can cancel out already lah. All right. I think ds also can cancel out. All right. So I got minus dp on ds minus rho g cos theta equals rho V dV on ds. Alright. Next step, you integrate this. Alright. Okay. Well, first I'll move all these terms to this side. So I have rho V dV on ds plus dP on ds plus rho G cos theta equals to 0. I integrate this from point 1 to point 2. Alright, well, integrate 0 from point 1 to point 2 is not going to be very exciting. Okay, so here, integrate this with respect to ds. Alright, okay, integrate this. So, this one should become okay, so this ds will cancel out this ds. V dv integrate becomes rho v squared on 2. Is that right? Actually, this ds will cancel out this one. So it's just v dv. V dv integral becomes v squared on 2. Is that okay? Alright. dp ds integrate becomes p. Alright, this one cancel out, integrate. Okay? And this one, you get plus rho g cos theta s. S cos theta. Alright? Between point 2 to point 1 equals to 0. Alright? So, in other words, rho v at point 2 squared over 2 minus p at point 2 minus plus rho g s at point 2 cos theta is equal to rho v1 squared well, actually minus rho v1 squared on 2 plus p1 plus rho g s1 cos theta equals to 0. Alright? Is that okay? So, basically this equals to this. Basically this equals to this. So, can I say rho v2 squared over 2 plus p2 plus s2 cos theta is actually rho g h2. Is that okay? Alright. S2 cos theta is just h2. Is the height of 2. Is that alright? Okay or not? Alright. Let's say S is some distance. So S is some distance. Okay. If this was the datum, alright, this was say S. Okay. So S this is S, this is H, alright, this is cos theta. S2 cos theta is just H. Why not? Alright, it's the elevation equals rho v1 squared on 2 plus p1 plus rho g h1 equals to constant along a streamline. Okay, so recap. This is the Bernoulli equation. Alright, so basically Bernoulli equation like P, Taylor write the P first, plus rho V squared on 2 plus rho GH equals to constant along a streamline. This is Bernoulli. Alright, but sometimes you like, okay, but sometimes you like to write it in terms of, if I can divide through by rho G. Alright, P over rho G plus V squared over 2G plus H equals to constant along a streamline. This is the head equation. Head or energy head. Alright. Okay, so the same. Alright, so later on we will actually use more of the second one rather than first one, but now we use the first one, but they are both the same. Is that okay? Alright, and you can derive them from two ways, from from energy, alright, or from the dynamics, the F equals ma. And this is valid, okay, I recap again, valid for steady state. What else? Constant density. And what else? Steady state, constant density. I got one more, I can't remember. No energy loss. Actually, no energy loss implies no viscous effect. Alright? Means also implies irrotational. Alright? Because when you have viscous effects, shear stress equals to mu du over dy. Alright? When you have viscous effects, alright, that is energy loss. Alright? The shearing of the fluid, alright, gives you resistance, gives you like a drag, isn't it? Alright? You think of it, if these two plates, alright, okay, here you have a force times velocity, there's power going in, isn't it? Alright, where's the power going? Alright, remember this effect when we did earlier? Alright, shear stress equals to mu du dy. So you needed a force to drive, let's say you sandwich some fluid between two plates and you drive the top plate. Alright, you can work out what the force is to drive the top plate and so on. There's a force. Force and the top plate is moving at velocity. Force times velocity is power. Alright, power. Where's that power going? Alright, that power is going to viscous heating. Alright, so that's loss. Loss. And energy loss. Is that okay? So we cannot have any shearing of fluid. Shearing of fluid will result in energy loss. Is that okay? So places where there is any velocity gradient, so that's why this one, no viscous effects or irrotational, means they all mean the same thing. They mean that if you have any viscous effects, any gradients in the flow, there will be losses. There will be losses. This one not valid. Okay, not? So this is only valid when everything is moving at the same speed. Side by side, everybody moving at the same speed. Alright? If they're moving at different, if the fluid side by side moving at different speed, they'll rub, it's like your two hands rubbing together. There will be, you can feel your hands getting hot. Alright? Okay, that goes to viscous heating, goes to losses in the fluid. The liquid here will get hotter. Alright? Okay, because energy doesn't disappear, it just transforms from this power to heating power here. Okay, any questions so far? So that's the theory or the derivation part. Okay, let's do some example. Alright, so again, you can use these two. Alright, you can use either form, it should be okay. Alright, I think the first example they use quite simple one. Alright, there's pipe 1 and pipe 2. Okay, the water here. Alright, so normally in a big tank, okay, in this unit, all the tanks are big one. There are no small tanks. Okay, in the big tank, the velocity about 0. Okay, so normally, alright, you can have to apply it along a streamline. So where does the streamline start? Well, the streamline could go all over the place. Alright, okay, so we choose to start one, we assume one of that streamline will start very close to the surface. Alright? But some of you might think, the velocity is 0, how the fluid moving? Okay, very, very, very slowly. Okay? So, away from this tank, alright, has these two openings. Away from this opening, the velocity is very, very slow. Alright? And one of the streamlines will go all over the place. Alright? One of the streamline will reach here. Is that okay? And this point we know. Let's say this here. We know P equals to P ATM. Okay? Other points you don't know what the pressure is. We know V equals to 0. H equals to maybe 3 meters. Alright? This one maybe 1 meter. This one maybe 1.5 meter. Okay? Maybe this one put 0.5 meter. Okay? Alright? So, when you start in the big tank, always start at the surface because you know what the pressure and the velocity and all that is. Pressure is the, whatever pressure in the tank, in this case atmospheric. Alright? This point, what's the pressure? Again, we're not inside the pipe. Don't do inside the pipe because we don't know what the pressure inside the pipe. As the water just exits the pipe, what's the pressure? Atmospheric. Alright, because the water has joined back the atmosphere. Okay. H is in this case 1.5 meters. And pressure, height, velocity we don't know. That's why we want to calculate. Okay. Here same. Pressure equals, so I call this point 1. I call this point 2. I call this point 3. Also ATM. H equals to 0.5 meters. Find velocity. Alright. So we apply Bernoulli equation. That one very easy. Which one you prefer to use? Okay. The units are different. This one, the units are in Pascal pressure. This one, the unit is in what? What's the unit for H? This one, the unit in meters. So that's why it's called a head, a length scale. Alright? Pressure head. P over rho G is pressure head. This one is what is this? This is the kinematic or kinetic head, and this is the static head. Okay. Alright. So I'll come back to that again after we do this problem. Okay. So the other okay. So in this case, alright. Okay. So in this case, what is it? So P over, which one you prefer? First one, okay. Bernoulli equation. P plus half rho V squared plus rho G H for point 1 equals the same thing. P plus half rho V squared plus rho G H for point 2. Okay. Alright, so that's the spot. Okay. So point 1, P atmosphere is equal to P atmosphere. So this is water. Okay, water. Alright, so P atmosphere plus half rho 0 squared plus rho G H in this case is 3 meters is equal to the next one, P atmosphere plus half rho V squared, which you want to find, plus rho G H is 1.5 1.5 meters. Okay, so this one can cancel out, this one is 0. Alright, so can I say half rho V squared is equal to rho G, this fellow move over this fellow, 3 minus 1.5. Okay now? Is that alright? Okay, this person move over to the other side. So in this case the rho can cancel out, so it doesn't actually matter what liquid it is. V is equal to 2 times 9.81 times 1.5 square root equals, what's the answer? 5.442 meters per second. Quite fast already, huh? So this is the ideal case. When you got no energy losses, it will come out at 5.42. Realistically, it's going to be less than that now. All right. Actually, you can do the same analysis for the second point. All right. 1 equals to, I'll leave you to do that one. All right. The answer for that one, okay, you go through the same step. The only difference is instead of 1.5 meters, is 0.5 meters. So V is equal to 2 times 9.81 times 2.5, the half. What's the answer here? You can do the second one, do exactly the same, except from 0.1, 0.3. Everything is the same, except the only thing is the difference is 0.5. What's the answer? 7? 7 meters per second. Alright? Everything else is the same. The only difference is this part, the 1.5 is different. It's now 0.5. And then you can simplify it to this. So, if your hole was here, it will come out at 7 meters per second. If the hole was here, it will come out 5.42 meters per second. Is that okay? Alright. Okay? So, what should we do next? Alright. Just now I mentioned, I myself do that one now since I mentioned it. Okay. In terms of head, plus b squared on 2g plus alright. So this one, you can call this the static pressure or static pressure head. This one, alright. This one, the elevation. This one, no, dynamic. Alright. Sometimes they call these two terms together. Alright, because these two parts, these two terms, alright, are actually the static component. This is just due to the elevation. This is just due to the internal pressure. So there's nothing moving in these two parts. It's only this part, the middle part, where it's the dynamic. Okay, so those are the names. Okay. Alright. So let's do another example before we talk a little bit more. Okay. Okay. So this example, okay. Alright. Let's say the flow comes in here at 1 meter per second. Area equals to 1. Alright. Flow comes out here. Area equals to 0.01. Okay. So what should the velocity be here? Alright. So rho A1 V1 is equal to rho A2 V2. Okay. That's for control volume. Okay, that's the control volume, and this is our streamline. Okay, so this is 0.2, this is 0.1. Okay, so by right, rho is the same. So area 1, velocity 1 is equal to area 0.01, velocity 2, 100. Oh, that's very fast, huh? Maybe I shouldn't do that one, huh? let's not go so thing. Maybe put 0.05. So 0.05 V2. Therefore V2 is equal to 20 meters per second. That's about 76 kilometers an hour. Still come out very fast already. Alright. Alright. Okay. So if let's say P1, the pressure is, let's say 100 kPa, what's the pressure at P2? Z1, I don't know what Z1 is, but all I know is equal to Z2. Okay? Z2, but I know is Z1. It's the same elevation. It's a horizontal pipe. Okay? Is that alright? So let's try to estimate what P2 is. P on rho G plus V squared on 2G plus Z. Alright, at point 1 is equal to P on rho G plus V squared on 2G plus Z2. Point 2. Okay? So P on rho G, here we have 100 kPa, 100,000. Again, this one assume water, so it's 998 over 998 times 9.81 plus velocity squared is what? Velocity here is 1. 1 squared over 2 by 9.81 plus Z1 is equal to P on 998 times 9.81 plus velocity squared here is 20 squared on 2 by 9.81 plus Z2. Z1 Z2 the equal, so they can cancel off. So the pressure equals to 100,000 divided by 998 times 9.81 plus 1 squared on 2 by 9.81 minus 20 squared on 2 by 9.81. Is that alright? Okay? So, equals, what is it? Oh, sorry, this whole thing must multiply by 998 by, actually 9.1 can cancel out. Sorry. Okay. So equals what? Right. So the pressure actually decreased. What is actually happening in this case? All right. You're converting flow energy to kinetic energy. All right. Sorry. You're converting, flow energy to kinetic energy. All right. What's the answer? Yeah, yes, could be negative. Huh? Negative 99.1 200 Pascal. Okay. All right. So it can be negative because this could be absolute. This could be gauge pressure. All right. All right. Okay. Okay. If you don't like negative, never mind, I won't change anything. All right. Let me settle down, please. So let me explain one thing here. All right. So basically, quiet, please. Earlier, all right. Earlier you converted potential energy to kinetic energy. Okay or not? Because higher you had potential energy. You lost some potential energy and you got some kinetic energy. Here, we've converted pressure, which is flow energy to kinetic energy. All right, we lose pressure. Pressure from positive 100 kPa, this will be gauge to minus 99. So it's nearly vacuum here. All right, minus 99 kPa. All right, that's why I didn't want to go too high. All right, because then your pressure might go below zero absolute. Okay, so P2 is equal to minus 99 kPa. These are gauge. Right, so 99 kilopascal below atmosphere. Is that okay? All right. So one last thing. This one, don't worry. We don't have any. We won't talk about the maths. All right. So we want to. Before that, I'll show you some application. All right. Maybe we finish off here, lah. Okay. So basically, this one. All right. You by funneling the flow like this. All right. Quiet, please. If I had a pipe here and a bottle here, okay, and some liquid in here, I could suck the liquid up, isn't it? And spray it out here. Okay, right? Because we generate such low pressures here. Is that okay? Yeah. All right. So this is used in this type of perfume spray bottles. Okay, I think there's a straw going down here. So you hand pump this one, the air goes into a small chamber, so the speed goes up a lot, the pressure drops, all right, and then sucks up the liquid, and that liquid and air, the mixture comes out in a spray. Is that all right? Okay, another example, you've seen before, wasn't it, a spray gun? All right, some have the spray can above, some have the spray can below. Same principle, all right, okay. The air from the compressor gets fed into a very tiny pipe here. All right. Within this chamber, the pressure drops significantly enough to suck the liquid up and spray out. The what comes out will be a mixture of liquid and liquid droplets and air. Okay. All right. I think I should stop here. We'll do the last part, the other story later on. Okay. Okay, so save.